Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the third lecture for week number 10 of our course of communication systems. In our previous lecture, we talked about the binary modulation, baseband modulation, which is is named as pulse code modulation. In order to achieve the pulse code modulation, we have to pass the analog signals from the different processes, namely the sampling and quantization and encoding, in order to generate pulses corresponding to the information contained in that analog signal. In today's lecture, will be starting our discussion with the pulse modulation, which is actually related to the M-array signaling for representation of information in form of pulses. So in pulse modulation, actually we present the binary pulses in order to we change some parameter of the binary pulse in order to represent the information that need to be transmitted. The primary benefit of transmitting the information by these pulses is that we get noise tolerance in the signal, because these are represented by discrete number of pulse levels. Secondly, we can also we also get the ability to regenerate the pulses whenever the signal is degraded. So we can use regenerative repeaters to regenerate the information when required. So how the information can be represented in form of pulses? In order to represent the information in form of a pulse, actually we need to change one of the parameter of pulses. There are number of parameters in the pulses that can be changed. So there is a possibility that we change the amplitude of the pulse to represent the information. So this type of modulation, where the information is represented by changes in the amplitude, is named as the pulse amplitude modulation. However, we can also change the width of the pulse or duration of the pulse. So if we are representing the information in form of pulses by changing width of the pulse, then the modulation scheme that is achieved is named as pulse width modulation, or sometimes we call it pulse duration modulation. The term duration is analogously used with width. Another possibility of representing the information in form of pulses is that we use different position of the pulses to represent the information. So we place the pulses at different positions to represent the information content. So this type of scheme is called pulse position modulation. So these are the three major categories of pulse modulation that are commonly used for pulse modulation. So let me graphically illustrate these three types of modulation schemes for pulse modulation. So let us take, we have an analog input which is represented by this waveform here. Of course, before representing the analog signal in form of pulses, we need to sample and quantize signal. So let's say sample it with a sampling time represented by t. So we get those samples here. These are the sample values that are represented here. These sampled values may be quantized and then they can be represented by number of pulses. So if we use the amplitude to represent the information, that is, if we want to have the pulse amplitude modulation, in that case you would see that the amplitude of the pulses would be according to whatever amplitude of this analog signal is there. You can see that the higher amplitude here is represented by a relatively higher amplitude of the pulse. A relatively low amplitude here is represented by the low amplitude of the pulse. And you can see that the simple information can be extracted by comparing the amplitude of the pulses. The waveform actually follows the amplitudes of the pulses, which are represented in pulse amplitude modulation. However, if we use pulse width modulation or PWM scheme, you can see that the amplitudes, they all remain the same. There is no change in the amplitude. Rather, we change the width of the pulse. You can see that the higher amplitude in the analog signal here is represented by a relatively wider pulse, whereas the low amplitude is represented by a relatively narrower pulse here. So you can see that this pulse is relatively narrow here, and whereas the for high amplitude we are using a wider pulse. So this width of the pulse is actually representing what is the amplitude of the modulating signal or analog signal here. Similarly, for pulse position modulation, we use different positions to represent the signals. For higher amplitudes, the pulses are displaced towards right, whereas for low amplitude, the pulses are displaced towards left. So the position of the pulse, this position is set according to the amplitude of the analog signal. So by comparing the positions of the pulses, we can extract the information which is contained in the message signal. So for PM signal, we use series of constant width pulses whose amplitude vary in accordance with the analog signal. Whereas for the pulse width modulation signal, we use binary amplitude. That is, there are only two amplitude levels. There is high voltage or low voltage, but the width of the pulse depends on the information signal. So the width or time duration of pulse is changed to represent the information contents. Similarly, for pulse position modulation, we generally use a very narrow pulse, but its position is changed according to the amplitude of the analog signal. Of all these types of the pulse modulation scheme, the pulse amplitude modulation is actually easier to implement. Is very simple scheme, and it is relatively less expensive as compared to the other schemes. So that is why it is very commonly used in many different applications. So this was the discussion that we started in the last lecture regarding the baseband communication. So baseband signals, they can be represented in form of pulses. However, we can have bandpass signaling incorporated in digital system as well. For that, we need to use a carrier. So we have some digital carrier modulation schemes as well, in which we use a sinusoidal carrier in order to represent the information contained in the digital information. We know that for sinusoidal carrier, there are three important parameters that to represent the information contents in the signal. So those three parameters are amplitude, frequency, and phase. So in order to represent the binary or digital information by using sinusoidal carrier, we need to either change the amplitude of the sinusoidal carrier, or we need to change the frequency of the sinusoidal carrier, or the phase of the sinusoidal carrier. For the case of digital modulation, digital bandpass modulation, we generally name these modulation schemes as shift keying. So all these schemes, they are named as shift keying. So there are three basic types of digital modulation schemes, which are amplitude shift keying, frequency shift keying, and phase shift keying. As the name indicates, each of the scheme represent what parameter of the carrier is changed to represent the digital information. For amplitude shift keying, we change the amplitude of the carrier. For frequency shift keying, we change the frequency of the carrier, and for phase shift keying, we change the phase of the carrier. So these are the mathematical representation for this shift keyings. So for amplitude shift keying, we need to use two different amplitudes. So if the modulated signal would be represented like this, so it will be having some specific amplitude, for example a cos omega ct, to represent the binary 1, whereas the amplitude would become 0 to represent the binary 0. So this you can see that the two waveforms, they differ in the amplitude. So both of them, they have different amplitudes. For one, the amplitude is a. For binary 0, the amplitude is 0. And of course 0 amplitude means there will be no signal that will be transmitted. So practically this signaling is related to whether you transmit or not. So if you transmit a waveform, that means it will be representing binary 1. If you do not transmit, so that will be representing binary 0. So that's why this modulation scheme is sometimes called on-off signaling, or sometimes we call it on-off keying or OOK. So in some cases this scheme can be written as OOK. It is worth mentioning that we are talking about the binary communication in this particular example. You can see that I have chosen the example where there are only two levels, one for binary 0 and one for binary 1. However, these shift keyings can be used for M array signaling as well. For example, if we intend to use 4 ASK signaling, that means if we are using the 4 levels, in that case there will be 4 different amplitude levels. So you will be having amplitude levels, for example 0A, 2A and 3A. So you will be needing 4 different amplitude levels to represent the 4 array ASK or 4 ASK. So the thing which I am presenting is just as an example, the case of binary signaling. However, it can easily be extended to the M array signaling. Similarly, if we talk about the frequency shift keying, so the frequency shift keying means we will be using two different frequencies to represent the binary information. So symbol 1 will be represented by one frequency, which is represented by omega 1 here, and symbol 0 will be represented by another frequency, which is represented by omega 2 here. You can see that both the waveforms, they have same amplitude, so amplitude remains same. They have the same phase, the phase is same. However, the frequency is different. So different frequencies, they represent different binary symbols. So one frequency is used for binary 1 and another for binary 0. Similarly, if we are using MFSK, that say for example 4 FSK, in that case we will be needing 4 different frequencies. The MFSK scheme can also be incorporated in the similar way, but in that case we will be having number of different frequencies to represent those symbols. And third scheme is phase shift keying, PSK. That means we will be using the same amplitude and same frequency, however we will only be changing amplitude. So you can see that we have a waveform which has amplitude A and the frequency omega c for both cases. However, for symbol 1 we have used the phase which is equal to 0. For symbol 0 we have used which is equal to pi. So this for PSK signaling, the information is contained in the phase of the sinusoidal carrier. And similarly we can extend this expression to M array signaling as well. So for example, if we intend to use 4 PSK. In that case, we will be needing 4 phases, say for example 0, 90 degree, 180 degree and 270 degree. So we will be using 4 phases and so on. So this scheme can also be used for M array signaling as well, by using the appropriate number of phases incorporated in the system. So graphically I can represent this information, these signaling schemes that I have discussed. You can see that the first is the binary code here, 101.001. It is represented by NR Z code at the top, which is the baseband signaling. 1 is represented by relatively high amplitude and 0 is represented by a negative amplitude. So it is a bipolar NRZ. So you can see that 1 and 0s, they are represented like this. If we represent the same binary information by using ASK signaling, in that case the 1 will be represented by a sinusoidal waveform of a specific amplitude and frequency. So you can see that all 1s, they are represented by these sinusoidal waveforms, whereas 0 will be represented by a 0 amplitude waveform, that means no waveform. So you can see that when we intend to transmit 0, there is no waveform there. So 0, the absence of waveform is actually representing the binary 0 for this particular case. For FSK, you can see that we need to use 2 different frequencies. We can easily observe that 1 is represented by a relatively high frequency, whereas the 0 is represented by a low frequency. Again, this 1 is represented by high frequency, the next zeros, they are represented by low frequency, and the 1 is again represented by high frequency. So you can easily see that whenever we receive the signal with a high frequency, that means it corresponds to the binary 1, whereas the reception of signal at a low frequency would represent the reception of binary 0. Similarly, we can use PSK modulation. For PSK, you can see that the 1 is represented by 0 degree phase, 0 phase. You can see that the phase is 0, the waveform is starting from here, and we can is represented by this waveform, whereas the 0, we see an inverted waveform. The waveform is out of phase by 180 degree. So you see a phase shift of 180 degree here. Again, for next one, you see a phase shift of 180 degree. Again, the phase becomes 0, and then for next 0, the phase is again shifted by 180 degree, and so on. So you can see that the binary 1 is represented by a 0 degree phase, whereas the binary 0 is represented by a 180 degree phase. So this was a brief introduction related to the bandpass signaling. So 3 main categories of bandpass signaling has been discussed in this part: ASK, FSK and PSK. Although I gave the example of binary signaling, but the same concept can easily be extended to the M array signaling. So let us now talk about some error detection and correction capability that we can get in the digital signaling, previously discussed as well. When we know that whenever the high speed data is transmitted over a channel, so it is generally contaminated by noise and interference and other unwanted phenomena. Those contamination, they generally cause the errors during transmission. So what happens if an error occurs during transmission? So actually that error changes the bit pattern. For example, if we talk about the binary communication, that means 0 and 1s will be transmitted. So if an error occurs, so 0 may be received as 1, and 1 will be received as 0. So 0 will be transformed into 1. So we will be having a different bit pattern as was transmitted. So if there are error during transmission, that means we will not be able to exactly receive the data which was transmitted. So that will result in the incorrect data reception. And eventually those errors, they are generally cause some bit error rate. So the performance criteria for communication that we commonly use is the bit error rate to understand how many errors they are occurring during the transmission. So we can use the some coding scheme in order to achieve some error detection and error correction capability in the digital communication. This process is generally named as channel encoding in the digital communications. So in channel encoding, what we do, we actually add some extra bits in the data. Those extra bits, they are actually, they do not contain any information. So they are non-information bits, but they are added in certain way, in a specific fashion, so that if there is an error, if there an error occurs during transmission, so these bits, they can be used to identify uh, those errors, or for the purpose of error detection or error correction. So one important thing that you should notice is that the channel encoding is actually adding some extra bits. So adding extra bits is actually creating an overhead on the system, because we need to transmit those extra bits as well along with the information bits. So as I mentioned earlier, that those extra bits, they are uh, they do not contain any information. They are non-information bits, and they are added for only error correction purposes. So from the information point of view, actually we are causing some overhead on the system in order to exercise control over errors. Typically, the channel encoding methods, they fall into two categories. One is the error correction codes, and other is the error detection code. Error correction and error detection codes, that depends whether the code provides you capability of detecting the error only, or it provides you the capability of detecting as well as correcting the errors without a retransmission. So let us talk about the error detection. There are many different methods that we use for error detection purposes for reliable communication. One of the easiest method is redundancy. That is, we try to transmit the message several times. So what we do, if we need to transmit 10 bits, so rather than transmitting 10 bits, we transmit 10 bits, then transmit the same 10 bits again, and then same 10 bits again. So we repeat the transmission. Until we are sure that the exact copy of the message is received at the receiver. So of course, although it's a very easy method, but of course it's a very inefficient method, because we need to transmit message multiple times, and it causes a significant amount of overhead onto the system. Another important method, most widely used method, is the parity. We actually add a parity bit in the block of a code, one addition bit which is added certain rule, certain assumptions, and that parity bit help us identify the errors which occur during transmission. Another type of scheme is called cyclic redundancy check. CRC is another mathematical technique used in synchronous data transmission, and which is very efficient for in removing those identifying those errors. It can catches up to 99.9% of errors. As I previously mentioned that the details of these codes will be discussed in the next semester course. However, in order to provide an insight onto the error detection capability, let us take a very simple problem of a parity bit-based detection capability. So let us take a simple problem in a single parity check code. So we have a single parity check code where a single parity bit is appended to a block of k data bits. We have a k data bit block and we are adding a parity bit here. You can see that the parity bit is represented by C. As I mentioned, we should add the parity bit according to certain rule. So this C1 is to be chosen in such a way that the code word satisfies the even parity rule. What is the even parity rule? Intuitively, the even parity rule represents that the whatever code word we would achieve, it should have even number of ones. So all the number of ones which are present in that code, if you count them, that you should get an even number. So that is the even parity rule. Mathematically, the even parity rule is represented by this expression that if we XOR all the data and the parity, so the XOR result will be 0. This is XOR operation. So this is the general case. So let us take k is equal to 3. That means there are 3 data bits and we are adding one parity bit. So we get a 4,3 code. 4,3 illustrates that the code word is of length 4, whereas out of 4 codes, 3 bits they contain the information, and the last 1 bit it does not contain any information. So we would try to generate all possible code words in this 4,3 code, and also we would try to identify which of the error patterns they can be detected by this 4,3 code. So let us start. Because we are using 3 data bits, that means there are 2 raised to power 3, which are 8 possible data words which are available. So data codes are here. You can see that data codes can be 000, 001, 010, 011, 100, 101, 10, and 1. These are the 8 possible data words that can be used. What should be the parity bit? You can see that this one does not have any 1, so you can we should add a 0 parity, because we are using even parity rule, that so that the total number of ones should be an even number. So the code word would be 0000. So we will be having all zeros. For this 001, you can see that we already have one binary 1 here. So in parity bit we will add another one, so that the total number of ones they become 2. So 2 ones is an even number. So the code word would be 0011. For 010, you can see that we already have one binary 1 here. So we would add another in the parity bit, so that the total number of ones becomes 2. So this one becomes 0101. Similarly, you can see that the next data word is 011. This one already have 2 ones here, which is an even number. So we do not need to add another one. So the parity bit should be 0, so that the total ones should remain at 2. And so on. You can see that we have added the ones appropriately, and the final code word always have even number of ones there. Okay. So how many error patterns it can correct? You can see that if, say for example, if an error occurs in one of the bits here, you can see that, say for example, if the 0 turns into 1. So if 0 turns into 1, you would see that the total number of ones would become odd number, 1 1 0. So having an odd number of ones would indicate that it has violated the rule. Eventually there is some error. Or say for example, if this 1 becomes 0, of course if 1 becomes 0, in that case the total number of ones would again become equal to an odd number, which is the 1. So having an odd number of ones would indicate that there is an error in the transmission. So if whenever we have a single error, that single error would be detected by the receiver. However, if we get two errors, say for example this 0 becomes 1 and the another 0 becomes 1, so we get a 1 0 0 1, so it will be detected at this word 1 0 0 1 in the receiver side, because having two errors would not be detected by the receiver because it does not violate the rule. However, if we have three errors, triple error, it can be detected by this code. So this code can only detect single errors or triple errors. It cannot detect double errors. So this is the capability of this code. So this was a simple example in order to illustrate how a parity bit based error checking occurs in the data transmission. So let us now move on to the error correction. We know that there are actually number of efficient error correction schemes which are available for data transmission. Whenever there is a process capability of error correction in the code, that means we do not need to have a retransmission. So generally this type of schemes, they are called forward error correction, because it does not require any retransmission, so errors are automatically corrected at the receiver side. The two basic types of forward error correction are block codes and convolution codes. In block codes, actually the additional those non-information bits like parity bits, they are logically added. More than one bits are added by exclusively ORing all characters of the specific block of the transmission data. So there are number of bits which are added, no, parity bits which are added in the data by using this XOR operation, and on the basis of reversing that operation at the receiver side, we can not only detect the error, but also we can correct errors to some extent. So these additional bits, they allow correction of errors which occur during transmission. Similarly, we have another scheme which is called convolution code, which actually convolution code they generate a special type of codes on the basis of current data as well as the previously occurring data bits. So it actually convolves those previous data bits and the current data bits to generate a special type of codes which are not called convolution codes, which are represented by two different outputs, and those outputs are transmitted at the receiver side. And by comparing those codes, we can identify where the error occurs during transmission, and we can correct those errors, whatever errors occur during. So this was a brief introduction regarding error detection, error correction codes which are incorporated in digital communication systems. So we would conclude our topic at this stage. We have briefly discussed the fundamental areas related to the digital communication, and we have talked about analog to digital conversion, as well as baseband signaling, bandpass signaling, as well as the source coding and the channel coding are incorporated in digital signal. However, I tried to be brief during the discussion because the most of the details will be covered in your next semester course. So thank you all. Hafiz.